And I'm talking to you tonight about Servlet 4.0, which delivers HTTP2 to the Enterprise Java platform. And the slides for this are available at that link, which I posted in the chat as well. And I think this will be recorded. Is that right?
That is correct.
All right, excellent. Here is my plan for your time investment. I know it's a nice summer night. I guess you guys have some weather up there, but not just the same. I do appreciate you taking time out of your week to be with us here tonight. I'll start with a brief personal journey of how I ended up at Microsoft, which might be a surprising place for a Java professional. And I'm here to tell you that it's actually a very good place for a Java professional. Then I will talk a little bit about how we can get Java and Jakarta EE on Azure. And that ties in very well with my personal journey because that's the point of me coming to Microsoft, is for that purpose. Then we'll talk about HTTP2 and Servlet 4 and some other new features that are in Servlet 4. And then we'll have a summary. Here's my professional biography. I've been doing web development for as long as there's been a web. I had the very great good fortune to be an undergraduate at University of Illinois in the early 90s, and that is where the world's first graphical web browser took off. And when I graduated, it was pretty much the opposite economy for what people are experiencing now when they graduate, which is if you knew how to make HTML in any way, and this is HTML 1.0, mind you, nothing like what we have today, you pretty much could go anywhere you wanted. So I chose to go to Silicon Graphics, and that eventually led to me working at Sun. And so I'm moving from the client side to the server side, working on Servlet and JSF and Bean validation, lots of other specifications that are in the mix. And I moved to Azure in 2019. So that's my personal journey to the cloud. I'm going to give a quiz to the Philly people here. This is me, and second from the right. Does anyone know who these other gentlemen are and where I might be? No raffle here, just a... So this is the Phillies radio staff: Scott Fransky, Jim Jackson, and Larry Anderson, and I'm a huge Phillies fan. And I had the opportunity to visit them in the booth a few years ago, so that was my top Philly achievement. All right, let's talk. I mentioned starting out on the client, right? The birth of a big thing. So the reason I bring this up is that there's a lot of lessons to be learned in terms of building platforms that we will see manifested in HTTP and then also in HTTP2. First and foremost, the client, the web browser, was really the birth of the big thing. Working at NCSA and on the Mosaic browser, and the lesson I want everyone to take away from is this platform was successful in huge part, I believe, because it was easy to author for it. You could just basically copy and paste from view source, and things have gotten a lot more complex since then. But at the birth of a platform, it's important to keep things as simple as possible to increase adoption. And this is also the case with HTTP itself. The platform was engineered to be easy to implement. So the original HTTP specification was very, very simple. What I will talk to you about tonight with HTTP2 is a lot more complex. But part of the simplicity let you do very simple, fun things. So this is an overview of the very first web-based e-commerce application ever. This was something we did at U of I to cobble together the campus email to fax service with a local sub shop. Now, you know, this sub shop, Jimmy John's, is no way near as good as like the Thunderbird on Westchester Pike. I'll point that out, but that's a different story. So with this simple thing, we could have this CGI-BIN, which was also invented around the same time, which was basically a way to read standard input from the browser coming in and send back from standard output. What this would do is send an email to the fax service that would eventually just call the Jimmy John's and fax in your order. So it was a very simple thing, but it did serve as a kind of e-commerce application. And the underlying lesson here is the simplicity of the original HTTP 1.0 specification made it pretty easy for anyone to even implement an HTTP server and a parser as well. Back then, there was no JSON. There was just barely, there was XML, but there wasn't widespread XML parsers. So the parsing capability for building a server was pretty much what the underlying C language framework provided, which is pretty minimal. So that's why the original HTTP was built on top of the MIME mail format with name, value headers with a character return line feed, and then a bunch of text in the response. And most importantly, that white space had a very important meaning. It was what separated the headers from the body. And that's one of the things that's now different with HTTP 2. So the next thing I got to observe at the beginning was the birth of the monolith, Spring and J2EE. And J2EE came first, Spring came along shortly after, and addressed some of the problems that were in the EJB 1.0 spec, but were quickly corrected in follow-on specs, and now Java EE has all of those problems solved a long time ago. So it's a perfectly easy to use self-contained platform, and Spring is also that as well. But they're two different threads that evolved from the same idea. Then I got involved with Java Server Faces, which is a specification for building web user interfaces in Java EE. And this gave me exposure to being a participant in the web framework war back in the early 2000s, 2004 through 2013 or so. There was just a lot of different web frameworks that were doing things, and participating in the JSF side gave me the ability to understand what makes another perspective on what makes a good platform. In the case of JSF, it was being easy to author, as I said before, but also having a solid cross-vendor thing. We had lots of different component libraries to choose from. So that's one of we were able to leverage the community to come together and work on this as one team. Then another big thing that happened was around 2004, Sun had this concept of utility computing, which was called the Sun Grid. It was way before its time in terms of general purpose cloud capability, and it really was at the wrong home. Sun made its money from selling hardware, and selling very specialized hardware as well. But the cloud is all about commodity hardware and scale. So it was the right idea, but at the wrong home. Before its time and at the wrong home. So now, after all those different journeys, I'm ready to work for the cloud. I wanted to get out from inside the monolith and work on the hosting platform for both monolith and microservices. And that's part of what I'll be talking about today. So the next aspect of the presentation is to talk about our current offerings with Java EE on Azure with Oracle WebLogic. So Oracle WebLogic is a Jakarta EE compatible implementation, Jakarta EE 8 and also Java EE 8. And we have a number of offers that let you do this, and I'll be showing a quick demo. And it's not just for the purpose of pitching the product, it's also the runtime that underlies the HTTP 2 demo that I'll be showing today. So the idea is you go to the Azure portal and you choose to deploy a WebLogic thing, and you can choose Java EE 8 as the runtime platform, and this will spin up a cluster, if you like, of an admin server with managed server VMs behind it, and everything is provisioned for you in a matter of about 15 minutes. We have 4 offers in the marketplace currently. You just go to the marketplace and just type WebLogic, and you'll get to choose from those. Another work stream that we're doing is WebLogic with Azure Kubernetes Service. So Oracle has a Kubernetes operator for WebLogic, and we will be using that to deploy kubectl and Helm to provision one of these Kubernetes clusters with WebLogic already built into it. So those are the links to the two different operators for the WebLogic side, and those are generic Kubernetes operators. They can run on any Kubernetes platform, but certainly for us at Microsoft, we are focusing on the Azure platform, Azure Kubernetes Service. So I'll start out with a demo, and it's not a very flashy demo at all, but I do want to show the point that I'm trying to get across here. So let me exit the presentation and go into the browser, and here is the portal. So you would go to Home, and you would just type, as I said, WebLogic in here, and you could choose cluster, for example, and then you click on Create. You have a lot of documentation support, and here is the magic that lets us get to Java EE 8. One of the WebLogic images you can choose from is WLS 14, which has WebLogic on it. I'm sorry, which supports Java EE 8 and therefore Servlet 4.0. Also notice that you can have a choice of several different JDK versions. We'll be expanding this list going forward, but you can for now choose 8 and 11 for the platforms. Another thing you can do is choose different Azure service integrations. You can deploy an app gateway. You can connect to a database that's already provisioned. You can use Azure Active Directory as the backend security realm. So I have already done this and deployed an admin server. So if I go to my resource groups, I'll show you what that looks like. Here it is. Okay, so I chose a very simple deployment, just the admin VM, and it creates a network security group for you and sets up the storage account and exposes a public IP. So if I click on this admin VM, I can get the DNS name of the public IP here, which is the familiar WebLogic admin console. So let me log into this. Okay. I hope this is a good size. Is the font too small?
It's a bit difficult to read on my screen, but I can make it out.
There you go. That's got to be better. So this is WebLogic running on the cluster, or running on the Azure service, that is. And I have deployed a number of sample apps. So I'll be showing two of them, just the Servlet HTTP2 and Servlet mapping. There's a few others. I have Prime Faces also deployed here and a simple shopping cart app. But the first one I'll show is the HTTP2 one. So let me close the... All right, so I'll talk about this in more detail later, but the basic way you get into HTTP2 is something that's called Application Layer Protocol Negotiation, ALPN. And it is a feature in TLS version 1.2. So that means if you go to a HTTPS URL during the SSL handshake, there's actually a HTTP protocol negotiation that happens as well, where the server can tell the client, hey, you know what, I support HTTP2, and the client can say, oh great, so do I, and then you get to use the HTTP2 protocol. And this very simple demo just shows you the image below was pushed using HTTP2. Server push is one of the big important features in HTTP2. Now if we go to the non-secure URL, just HTTP, and I have to change the port to 7001, you can see this, the image below was set normally using HTTP1. And the reason that works is this bit of code, which I will show right here. Pardon my use of Emacs, it's just easier for this context. So Here we go. So what this very, very simple servlet does is asks the HTTP servlet request, do you have a push builder? And the specification says if you don't support HTTP2, then just return null. So that's how this thing tells. So if it's null, then we just write out the image link. Otherwise, if it is not null, we use the response. We add an HTTP2 protocol header, and we put some text out, and then we use this HTTP builder, push builder thing, and send the logo directly. Now this is a very simple example, and I like it for that purpose, and I want to share the GitHub URL for this. It's just Java EE8 samples. Java EE8 samples. If I search for it, it should be the first hit. Yes. So this is my colleague Manfred Ream, who also joined Microsoft almost exactly to the day as I, about a year ago, and we worked together on JSF as well at Oracle. But this, I want to give a plug to these samples because it does just give you a very simple view, the simplest possible view, with for all of the different sub-specifications in Java EE8. Okay, another feature for the demo that I'll show is the servlet mapping feature. So prior to Servlet 4.0, there was no way for the executing servlet to know exactly how the servlet was invoked, what mapping. So with the Servlet API, you specify how you want the URL to suck in or apply to a servlet. So there's extension mapping, there's prefix mapping, there's exact match. So here is one where I'm showing that it's using the extension mapping, but if I change it to just remove this, this is the context root mapping. If I go and say exact, that's the default match right there. And so that's another simple example, which I'll show the source code now. It's this one. So there's no web.xml for this servlet because it's just everything is coming from the annotation. And you can see you can just declare what are the mappings that you want to apply your servlet to. And here you can ask the request, hey, give me the mapping for this thing. And that's what it's just printing out. Mapping, mapping, match, and then appending those writers. So this system out println goes to the log, and this writer goes to the response. So those are the simple HTTP2 demos that I'm giving, and I can talk more about the demos and other... Oh, actually, no, there's one other thing I wanted to show you to verify it does work with push right here. So if I go back to HTTPS, let me turn on Developer Tools and turn on Network, and I will reload the page, disabling the cache. Okay, and here's the logo, and you can see it doesn't say anything about HTTP2 there. So if you view source, in fact, it will tell me, oh, this is HTTP 1.1. Okay, so now if I go to the HTTPS version, 7002, where is the image? Let's reload it. This is interesting. When I was doing this earlier, let me try one more time. Yeah, the initiator would show push test. I'm not sure why it's not doing that now. It would show the initiator would be sending the image. Well, you can see that we don't see the HTTP1 response there. So it is coming over as HTTP2, but it should be pushed. Maybe there's a caching thing. I'm not sure why. Try this. Index. No, I'm not seeing the push. Initiator. That's really weird. I tested this just before the demo started. but you should see push here, and I'm not sure why that's not showing up. There must be some network client thing that I'm experiencing. Well, I will explain a lot more detail what push is and why it's an important feature, but I wanted to get the demo out of the way first. So let's go back into the slides. I accidentally selected from beginning. Here. There we go, from current slide. There we go. So with web browsers, perception really is reality. This is the first page of the RFC for HTTP2. And you can see here that right on the first page, it wants to give users a reduced perception of latency by introducing header field compression and multiple concurrent exchanges on the same connection. So that's how that's where the HTTP2 magic is, and it's all about the reduced perception of latency. Because the main stakeholders in driving HTTP2 were really Google, a few other vendors as well, but their business relies on having things delivered very fast. And there's lots of studies, of course, that show if you're trying to deliver ads, the longer you have to wait, the more people will just drift off and you won't be able to convert them, to use the marketing term. Let's do a quick programming review. HTTP2 is really just a new transport layer underneath the HTTP 1.1 protocol model. So they took the API and lifted it up and put another layer underneath. It has the same request response model. There's no new methods, get, put, post, head, all of those are the same. There's no new headers. The way you specify headers and encode them is very different, but the set of header names is the same. There's no new usage patterns from the application layer. It is still a request response protocol. And there's no different usage of the URL spec. So it was a very good example of building on the shoulders of others. Let's do a quick network programming review. This is the Stevens Unix network programming book. I think it's still important. So we have the 7 layers of the OSI protocol stack. And HTTP2 is an application layer protocol, but it introduces a concept of a connection, which is something normally found in the transport layer. So it kind of imports that concept into the spec. It also introduces a concept of frames, which is something they took from the network layer. And it also introduces a concept of streams, which is something they took from the session layer. And then on top of all of that is the regular HTTP 1.1 spec that everyone understands now for many years. So let's talk about the socket angle. In HTTP 1, sockets were a throwaway resource. The specification says very little about how sockets are supposed to be used. Browsers are free to open as many sockets to the same server as they want. In practice, this was limited to like 8 usually. And sockets are an expensive OS resource, so there's been a lot of sort of optimizations to enable sockets to be used more wisely. But all of these could only go so far, because to really optimize things, you have to go down to the protocol layer. So in HTTP2, however, the specification says very much about how they're used. With HTTP2, you're only having one socket open per server. So it used to be a browser would visit a website and open like 8 simultaneous sockets so it could suck things down at the same time. And that was a very expensive way to do things. So it was basically imagining combining all of those simultaneous things into one stream. But when you do that, you have a lot of other problems you have to solve too. And I'll cover that later. So we've covered sockets. Now let's talk about the adoption angle. This is what I mentioned at the beginning of the talk in terms of building a platform that goes well. HTTP 1 was designed to be easy to implement with contemporary development practices of 1991. So that's a long time ago. But at the time, the state of the art was, text-based protocol, doesn't worry about flow control, leaves that to the TCP layer, easy to write a parser, given only a very meager set of libraries, usually what's provided by the language itself, and it had a very simple socket life cycle. Open it, use it, close it, throw it away. HTTP2, on the other hand, is much more complicated to implement. It requires a state machine, it requires flow control, it requires a way for you to do header compression and binary framing. Now, the nice thing about binary framing is you don't need a parser for that either. You actually just know the number of bytes in the protocol, and how many bytes each segment of the frame takes. So there is no parsing there. So in that sense, I think it is easier than a text-based parser. These are the big ticket features in the HTTP2 spec itself. Request response multi-framing, the binary framing I talked about. Since you have binary framing, you can have multiple streams open at the same time, which means you need a way to prioritize them. So the client knows which ones to give more attention to. Header compression and upgrade. How do you get into it in the first place? So we're going to talk about each one. The request response multiplexing. The idea is to let the protocol do more things with a single TCP connection. Now, TCP sockets are always bidirectional. In HTTP1, you just pretty much the client always reads from the socket. In HTTP2, there's more back and forth. This multiplexing is enabled by defining some terms. So in the spec, a connection is a TCP socket, a stream is a channel within the connection, a message is a logical message, such as a request or response, and a frame is the smallest unit of communication in HTTP2. So nowadays with reactive programming, they call these capabilities back pressure, but a more accurate historical term, I believe, is to call them flow control, because that's what they call it in TCP, and that's really what it is. So this is a visualization of that previous arrangement of things. You can see we have multiple connections depicted here, and within each connection we have multiple streams, and within each stream we have multiple messages, and the messages are each composed of a number of frames. Now, once you break that communication down into frames, you can interweave them, and then they're reassembled in the correct order at the destination. So the request and the response can flow down in whatever order they're ready, and the client or server can reassemble them using the proper ordering that is baked into the frame with the stream ID here. So you can see here, headers always must precede data. So stream 7 headers, stream 7 data, that's going from the browser to the server, whereas stream 4 is coming from the server to the client. So this is stream 2 headers, stream 2 data, and stream 4 headers is next. The thing that's also an optimization from TCP here is that streams originating from the client all have odd number stream IDs, and streams originating from the server have even number stream IDs. So this is a very simple and effective way to disambiguate the two things. This is what a frame actually looks like. You have 24 bytes, a 24-byte integer that is the length of that represents the length of the frame, including the headers and payload. A type, 8-bit type. I said bytes. I meant to say bits. 8 bits of type information. These are the different types that tells what kind of frame this thing is. Then a 31-bit stream identifier with a 1 reserved bit at the beginning, and then the remainder of the frame is the payload. So that's a binary representation of whatever it is, image or text or whatever you have. And this approach with the stream identifier solves the head of line blocking problem. So the head of line blocking problem briefly is, let's say a browser is requesting a page that has 2 images and a style sheet and a JavaScript file. With head of line blocking, they have to be delivered in the order that they are encountered in the parser. So 2 images and then the CSS and then the JavaScript file. With multiple framing, they can all be delivered in whatever time the server is able to deliver them, and then they're reassembled in the proper order on the client. So this is a way the browsers can speed things up. They can render what they have instead of waiting for things to come in the order in which they're specified in the page. Another optimization is header compression. So with HTTP1, you have to send the same headers every time, even though from request to request within the scope of one session, say, there's a lot of similarity between the two. So and they're delivered in text. So there's a lot of wasted information. You know, the user agent is always the same, but it is sent every time. With HTTP2, what happens is they keep a table of header IDs, and they have also these notions of implicit headers that are specified in the specification, and that enables there to be much less header traffic. You're not reusing things. Now, it's not really compression. You know, there's no like lempel ziv or any other kind of compression algorithm. It's just by using this binary protocol where there's a state machine on either side of the connection that this compression is able to be achieved. Another thing is the priority header. So these are the stream IDs we have here, A, B, C, and each stream ID is assigned a weight. So this is supposed to be interpreted by the client as a percentage of the compute resources that are to be handled here. So B and C, C should get 3 times, or yeah, 3 times as much resourcing as B gets. That's what this specifies. And then you can also specify an exclusive bit. If the exclusive bit is set on the stream, then it is processed first, and then the remaining streams that are not set with the exclusive bit are used with the priority mechanism that I mentioned before. Server push. This is a big one for optimization. So before push came around, browsers did a whole bunch of tricks to make things fast. They had what's called domain sharding, which was a way to basically trick the client into thinking that it's talking to multiple servers, so it will open more sockets. But in fact, on the server side, it's the same server, because the server has been provisioned with enough sockets to handle the load. You don't need that anymore with server push. Another trick was resource inlining. So you would base64 encode your images and put them in with data colon URLs in the page. That would ensure that they came down very quickly. You can think of server push as basically letting the server populate the browser's cache in advance of the browser asking for the resource to put into the cache. Without server push, the browser only knows what is in the page. With server push, the server, which has a priori knowledge anyway, can sort of tell the browser, you know what, you're going to need these things. Let me give them to you now. And then the browser can say, oh, all right, now I need it. And it's already in the cache. That's the idea. Finally, an interesting point here, how do you do the protocol negotiation, right? So there's secure or not secure. H2C, the not secure variant, is on port 80, and the specification says you're supposed to send a 101 switching protocols header, and then you would negotiate with the server to switch to HTTP2. No browsers actually implemented this. It's just not going to happen. The more common, and in fact only way in practice to get to HTTP2 is use TLS, ALPN. So as I said at the beginning, during the TLS handshake, there's a protocol negotiation where the client and server can realize both of them support HTTP2, and then they'll use that. So that's the basic aspect of the servlet spec. of the HTTP2 protocol. I'd like to pause a moment and ask if anyone has any questions about the protocol itself before I get into how Servlet 4 exposes that. James Purcell, as I remember, you could implement HTTP at the CDN layer with 0 changes at the origin layer. Well, yes, I mean, intermediaries can implement it for sure. But if you do it with an intermediary, you're missing out on some of the benefits that I'll cover in terms of server push. So, for example, if you have a web framework, such as JSF, the web framework itself knows what resources go along with which pages. And the web framework is the only party that knows that knowledge. Intermediaries don't know that. They just, they're passing data along. So in the case of the JSF spec, I'll talk about how we optimize that to take advantage of server push. That's all I see on the questions. Does anyone else have any questions, or should I continue on?
I do see a question here. How does HTTP2 differ from WebSockets?
Great question. Okay, WebSocket is an application protocol that has a W3C API as part of the HTML5 specification. So if you're building an application in Node, or in fact, there's a WebSocket API that's a part of Java EE 8 that has a client and a server piece too. But it turns out a lot of people nowadays, if they're using WebSocket, they're doing it using the W3C WebSocket spec of HTML5. There's nothing like that for HTTP2. Even the bidirectionality stuff, that's not surfaced at the application layer. HTTP2 is an application layer protocol from the TCP perspective, but the server push feature is not surfaced through HTML5, whereas with WebSocket it absolutely is. Any other questions? Okay, well, let me get right back into it. Well, the Servlet API is well positioned to enable these optimizations, and this ties into the question actually. It allows frameworks to effectively leverage server push and also implement flexible strategies for that too, and you're being able to leverage ALPN for the negotiation. So these are the features I mentioned, but these are the ones that these are the only ones we're exposing really in HTTP2. Server push, upgrade, and a little bit of flow control. So the big feature, simply being able to use HTTP2 was a big deal. And there was a funny little side story here, and I won't go into too much detail, but it shows the challenges that few appreciate when being the steward of a platform, as Java EE is. So Java EE 8 is defined as depending only on Java SE 8. So unfortunately, the ALPN feature was only available in Java SE 9. So, and this is a funny side effect with how long it took to deliver Java EE 9, mainly because of Jigsaw, the module system. That took forever to get completed because it was such a monumental, huge task. So we, in the Servlet implementation community, were stuck with having to do various workarounds to basically extract the SSL layer from Java SE 9 and use other kinds of implementation details to make it work, rather than allowing or depending on it being there in the platform. So this just basically made the life a little bit harder for the implementers of the spec. Another thing that it required was, providing an implementation for HPAC. So that's something we were able to get done. So the server push thing is, you basically push a resource to a client for a given URL and headers. As I said before, it's not a replacement for WebSocket, and it is very useful for things that build on top of Servlet, such as JSF or any other web framework. This is what the API looks like. You ask the request for a push builder. You can add headers and e-tags and all the different kinds of things. Set the path, and then you click push at the end. Or not click, you call push. This is what it looks like in UML. You have the browser send the GET request. The server discovers that the browser will need these extra things. In the case of JSF, that's because the page author has put those things in the page, but the framework knows about it. So it gets the push builder and pushes the style sheet and the JavaScript, and those resources start going down, and then it will push the page. So actually you get the resources before you start getting the bytes of the page in most cases. So here's an example. This is the stock Faces servlet from JSF. This is the thing that enables the JSF front controller to work. And it basically says if the handler is a resource request, we say handle resource request. Otherwise, it's a page request, and then we run the JSF lifecycle. Inside the is resource request, we have this call to encode resource URL, and here's where we push out the resource. So this enables every JSF application running on Servlet 4 to automatically take advantage of the server push feature without having the page author have to change any aspect of their code. And this is from JSF, but any other web framework is able to take advantage of the same technique as well. This is the reactive manifesto here. What it means to be reactive: you have to have these concerns addressed: responsive, resilient, message-driven, and elastic. And then you get to wear this reactive badge. What we're talking about in Servlet is really message-driven and responsive. So it turns out we already had this in Servlet 3.1. The on data available and on write possible methods enable you to do flow control correctly, which gives you some level of reactivity. In other words, back pressure. C for Servlet 4, we had some additional community features, Java SE8 default context methods. We added a default filter and a generic filter. We finally specified a default context path element in web.xml. We added a way to get the array of cookies from the servlet request. That was a nice thing to have finally. This is that servlet mapping feature I showed the demo of. So what you would do is ask the request, give me the mapping, and mapping has several different sub-values. This mapping match is an enum that tells you what kind of match it is, and match pattern and match value is, pattern is if it's a star dot something or something dot star, like foo.jsf, for example, or JSP. Match value would be, what the actual literal is that was handed to it. We did some deprecation of methods, and then we had some very small change, some clarifications, what metadata complete means, and so that's really, we went through pretty quickly. The summary was, for me personally, being willing to adapt and change your focus, moving from the server side to the cloud. And really the cloud has disrupted everything, and Azure is a great cloud for Java workloads. So that is the end of my presentation.